So, here at this part of your course, the part where you learn about inverse trigonometric substitution, you're probably learning a lot of other substitution methods, but this one's probably one of the more complicated ones. So, with inverse trigonometric substitution, we use it when we see radicals of this type, and we substitute these formulas, and we use this identity to simplify the integral, so we can integrate it. And this is just the restriction on u. So let's get started. So why do we need them anyway? These equations have many applications in engineering and physics. Knowing them will allow you to get a deeper appreciation of your field of study. Without this skill, you'll struggle to enjoy everything which your field has to offer. Trig is very important. Alright, let's have a look at our first case. A squared minus x squared. So if you see something of this form in an integral, you're going to solve it quickly if you substitute x for a sine u. So the way to remember it, because sometimes when you're in an exam you don't have time to flip to the formula sheet, is that if you see this negative sign, it's going to involve the substitution of sine, and this little curly s, the radical sort of looks like an s, so you can also remember that as sine. So, but obviously the best way to remember which substitution to use which is to do a few examples. So let's find this integral. So the first thing you want to do is to change the variables. So you recognize that this is of type a squared minus x squared. So we substitute x equals a sine u, and our a is 3 because 9 is just 3 squared. So we substitute in 2x, x equals 3 sine u. And of course, if we're going to do substitution, we do need to change our dx, and if we had limits, we would also do a change of limits, but this is an indefinite integral. So our dx du is just 3 cos u, and our dx is 3 cos u du. You also should figure out what u is, because at the end, once you've simplified the integral, you do need it back in terms of x. And if you have any other trigonomic functions apart from sine, like cos of u, you need to figure out what u is for cos, and you can use a triangle to figure that out. So after you figured all this out, you just substitute it into your integral. You simplify it. As you can see here, it's just 3 squared sine u, which is 9 sine squared u. Then you take the 9 out and you get 1 minus sine squared u, which you can just use the Pythagorean Identity to simplify to 9 cos squared u. And of course the square root of 9 and the square root of cos squared will just be 3 cos u. And as you can see, it will cancel out very nicely for us. And all we need to evaluate is 9 sine squared u du. And our sine squared u, this you need to use trigonometric substitution, just the basic one. So we do need to use a half angle formula. And if you've seen my last video, I explain a very easy way to remember it. So you go minus cos u, and then you take the constant out. That's all you need to integrate, and never forget that plus c with indefinite integrals. So there you go. There is your formula. Now, we can't substitute u back in because we don't know what sine 2u is. So we need to simplify that one further. Now sine 2u is just 2 sine u cos u. So it's okay. But how do we get this back in terms of x? Well, remember at the beginning how I explained how we might get different trigonometric functions and what we started with, and we may need to use our triangle. Well, this is the case. We've got cos u. So what is cos u? Namely, what is u equals cos minus 1. So we just use our good old primary school SOHCAHTOA to figure out where the opposite, adjacent, and hypotenuse is. Well, because our u equals sine minus 1 of x over 3, this is our opposite, so this is our x. This is our hypotenuse, which goes here. Then you use Pythagoras to figure out the missing side, which is just c squared equals b squared minus a squared. And so now you can figure out that cos of u is u equals cos minus the inverse of cos adjacent over hypotenuse. And there you go. And then you just substitute this back into our formula and simplify, and you're finished. Now I'd like to point out here that we have substituted an inverse function, and this is why this method is called the inverse trigonometric substitution formula. It's supposed to say trigonometric. That's it. All done. So you may think that, okay, that's pretty cool, I got the hang of it, makes sense. But sometimes in questions, this radical can be hidden in interesting ways, but it doesn't matter what form this appears in. It could be 16x squared, a could be 16x squared. It's still in the same form. Whenever you see this radical, always go for the inverse sign substitution formula. To prove my point, let's just do another example. You see there's an x squared there. Probably in an exam or test and you're like, oh no, I don't know how to do it. You do. Because look, this is our familiar radical right there. So, here we go, I've written it down. First thing to do, change a variable. So, identify the type, it's a squared minus x squared. Then substitute x equals a sine u, x equals 2 sine u, because this is just 2 squared. And then figure out the derivative, so you can change dx in terms of du. And of course, figure out your inverse, so we can substitute it in later. And then figure out your triangle, just in case we get different trigonometric functions. So, substitute it all in, and as you can see, we get our 1 minus sine squared u when we factorize the 4 out, which is just 2 cos squared u. And as you can see, we get them cancelling out, because this becomes 2 cos u. Yeah, that's not supposed to be a cos squared u, that's definitely 2 cos u, so they cancel out, and you get 1 over 4 sine squared u, du. And so, you can change this to cosec squared of u if you want to. That's what I would do, because usually in a test you get given a formula sheet and it will tell you the integration and differentiation of these types of functions. So this integrates to cot of u plus c, don't forget the plus c. So what is cot u? What do we do now? We just use our triangle. Whenever we're doing inverse trigonometric substitution, this triangle is what helps us through the question. So it doesn't matter if you get cot, cosec, or secant of whatever, you just break it down into the familiar trigonometric functions and figure it out. So what is cos u over sine u? Well, we could just figure out cos u and sine u and divide them, or we know that cos u is adjacent over hypotenuse and sine u is opposite over hypotenuse, so those just cancel out and you figure out adjacent over the opposite of the side. So cos u over sine u is a over o, opposite to tan u. So there's a few ways you can figure this out. There's like 3 ways. So it's okay. There's plenty of ways to do this. So you substitute all of that in and you find out that the integral of this formula is this. Not too bad. So this is all of the working out that we just looked at for, this was, I think, yeah. Why? Well, they're the wrong way around. That's fine. I think you can understand that this goes first, then you do this. This one's the right way around. So this is what we just did. So, the next one. This one, any integral involving this radical will be solved the fastest through substituting u equals atan of x. You can remember it by the fact the plus sign looks like a t. So if you're in a test or an exam, you know that a squared plus x squared, we'll just use this substitution. So let's do an example. How better else to understand things unless you have an example? But so while I was doing these calculations, I had a realization, an epiphany if you like. I will be using these formulas for my entire life because I'm going into electrical engineering and I know for a fact that these things appear just about everywhere. So I better know how to use them. Yeah, I better come up with a reliable way to remember them and make things a lot faster. So this is the acronym I came up with, VTPDIT. Very tired people die in tears. Yeah, no one's gonna forget that. So let me explain this with an example. So VTP, very tired people die in tears. What do I mean? So the first thing you want to do is a variable change. Then you want to figure out the type. So is it a squared plus x squared? Is it a squared minus x squared? Or is it x squared plus or minus a squared? What is it? You gotta figure it out. Then you put it into the formula. So you substitute it in. So x equals 3 tan u. And then you find dx of du, so you can put it in terms of du. And then you find the inverse because you need to, well, there should be a u there. Then you need to find the inverse, so you can substitute it later towards the end of your calculations. And then of course the triangle. So why does it say n? My goodness. I'm all over the place today. Very tired people die in, I don't know, some. Let me know in the comments. So if you get this right, it's easy to finish the rest of the question. There you go, you substitute it all in. You've got 1 plus tan squared of u. And I actually have a trick for remembering all of these interesting variations of Pythagoras and the secant, cosecant, cotangent. So essentially, to find the Pythagorean identity for tan squared and sec squared, you just divide everything by cos squared of u, and that simplifies to tan squared of u plus 1, which is equal to sec squared u. Now you're probably thinking, well, how am I supposed to remember that this is sec? Like, it has nothing to do with cos. So what I do is that, notice that all of these formulas, the third letter corresponds to the trigonomic function in the denominator. So that's how to remember it. Nice and easy. So you've substituted it all in, you've simplified it, you're having a great time. Now you get to this section. What is the integral? What is the antiderivative of sec u? You're going to have a look at the formula sheet in your test or your cheat sheet, unless the question wants you to derive that as well. So there you go. And then to figure out sec u and tan u, you use the triangle, and then you substitute this into the formula. And don't forget your plus c. So this is all of the working out that we just went through. Yeah, hopefully that makes sense. Feel free to copy it down. And yeah, remember, very tired people die in tears. That is going to help me through an exam, because I know for a fact I rush in exams, and if I follow this, then I'll be okay. So this one is a strange one. We don't have a squared first. Usually a would come first in the alphabet, but here x comes first. So you can just remember this one as a strange one, whatever helps you remember or memorize it. So this one is you substitute x as asec of u. So let's see the strange one in action. Remember that very tired people die in tears. And I hope I'm not scarring anyone. Okay, so let's integrate this integral. As you can see, okay, we gotta follow our acronym there. So the first thing, variable change. So, because the reason why you want to put the variable change first, I feel like I haven't explained this well throughout the video, but you can't just dive into integrating this until you do a variable change, because the variable change is going to allow you to simplify things. That is why we do the variable change first. And then we need to identify the type, because there are a few types of radicals that we can integrate through inverse trigonometric substitution. And then we put it into the formula. So x equals 3 sec of u. And then we find dx du. So we're up to die now. Yeah, I'm gonna remember this acronym. So you need everything in terms of du, and then you find the inverse, which is u equals sec minus 1 x on 3. And then you draw your triangle, just for later reference. And then the rest follows from VTP dit. So there you go. All the simplification done. I've explained how to find the Pythagoras theorem for sec and tan, so you should be okay with that now. All the simplification is there. Then after you've done that, did I do what I think I just did? I did. I'm not re-recording this video. This is a long video. So I'm going to re-explain this previous slide step by step. I did that on purpose, actually, completely on purpose. So you put in your x, which is 3 sec of u, and then you evaluate it to get 3 squared sec squared of u minus 3 squared. And of course put the dx in. I didn't have enough room to write it on the paper, so I just put it into the next step. And then you take out the 3 squared, so you factorize it, and then you find out what sec squared of u minus 1 is, which is just using the Pythagorean identity, and you find out that it's tan squared of u. And what a good habit to do is when you've got a long denominator and a long string of something you're multiplying with, put it on top of the denominator so you don't get confused in your test or exams. So you can just cross it off like this, and it's much more reliable. So there you go, you simplified it, you integrate it, you get sec of u, and this is what you have. Now, how do you find sec of u and tan of u? You use the triangle. So sec of u is just x over 3 because it's the opposite of cosine, well, sort of, and it's h over a, so hypotenuse over adjacent. Tan of u is just opposite over adjacent. There should be a u there. I forgot to put the u in there. There should be a u there. And then you have evaluated the integral. This is the last example for the video, because these are all of the basic inverse trigonometric substitution formulas. Any other radicals or any other forms of it are just they're just variations of the three that we just learnt. That's it. So now you should be able to understand what this table means, which identities you use, what the integral involves, why we use these, and so on. So well done. It's quite a video full of lots of information, so if you made it through to the end, give yourself a pat on the back. So my next video will be on integration by half angle substitution. If you want to check out my other videos on integration by substitution and trigonometric substitution, go ahead. I'll also be doing some videos on on integration of rational functions by partial fractions and integration by parts. I hope this video has helped you out.